Okay, everyone, we are going to start lecture 8.8, and this is just a review on graphing. So we will want to review graphing of reciprocal functions and then graphing of rational functions. Remember, a reciprocal function has the parent function f of x is equal to 1 over x, whereas a reciprocal function, a rational function will be some polynomial p of x over some polynomial q of x. So the parent function standard form will be in quadrants 1 and quadrants 3 with asymptotes that are the x and y axis. So we have x equals 0 and y equals 0. With the domain, similarly, all of x except for x cannot equal that asymptote. And the range being all of y except for y cannot equal its asymptote. The standard form that we did, saying, okay, well, we can definitely make this more complicated, as y'all know, and we can instead say that it is a over x minus h plus k, where h is the horizontal shift, and a positive value, if you see that there, will shift it left, which is counterintuitive, and a negative value will shift it right. So this value is the counterintuitive value. K is the vertical shift. That one's a little bit more intuitive. If it's a positive K value, then you'll shift your graph up. If it's negative, you'll shift it down. If A is negative, the function is reflected across the x-axis. So let's just really quickly draw that. Oof, that is a bright pink. I'm not sure if I can handle that this early in the morning. Okay. As opposed to being up in quadrant 1, it would flip across the x-axis, and this one would be in quadrant 4. And instead of being in quadrant 3, it would flip across the x-axis, and it would be up here in quadrant 2. So that is reflected. So if your value is negative, then you will flip it across the x-axis. Now, if the absolute value of it, so you've already determined whether it's negative, so if you're just looking at the value of the number itself, if it is greater than 1, then that will be a vertical stretch. And if it's less than 1, but between 0, obviously if it's less than 0, then now you're back to looking at reflections, then this will be a vertical compression. For the most part, we didn't really need to deal with these because I'm okay with you analyzing this standard form and doing the transformations as far as what are the asymptotes, how much is it shifting up and down versus left and right. Stretching and compressing for these graphs is really hard to show on such a small graph, like a 10 by 10 graph that we always have. Your vertical asymptote will be x equals h, and your horizontal asymptote will be a y equals k. So you can pretty much look at this standard form on your quiz or on your test coming up and learn what I'm going to want to know about these graphs, which is what are the asymptotes, is it reflected, so on and so forth. Let's do a couple examples. So for this, we can see that we are down 5 and we are left 1. So if I go ahead and on my graph, I draw my new asymptotes. 1, 2, 3, 4, 5. That has taken care of the +1 in the denominator and the -5 outside of the expression. And then our 1 up here means that there's no stretch or compression and that it's not reflected. So I can go ahead and just draw this like this. Perfect. We know that our vertical asymptote is x equals h, so that's a -1. And that our horizontal asymptote is y equals the -5. So our domain is that x can be all x except for x cannot equal -1. And our range is that y can be all y except for y cannot equal -5. For this one, Our k value is 0, so it's not shifting up or down at all, which means this will be our horizontal asymptote. And our vertical asymptote here will be left 3. 1, 2, 3. I have a reflection. So instead of being in the top right and the bottom left, I'm going to be in the bottom right and the top left. And it is vertically stretched by a factor of 2. So my vertical asymptote here is x equals -3, whereas my horizontal asymptote stayed the same. My domain is x can be all x, except for it cannot be that asymptote. And my range is that y can be all y, except for y cannot be its asymptote. So the key difference for you to realize for these problems is the difference of whether or not you're dealing with a reciprocal function versus a rational function. It is a reciprocal, or one of these easier hyperbolas, if there's no polynomial equation in the top of your fraction or in the numerator. So there's no x in the numerator, there's only an x in the denominator. If you have an x in the numerator and in the denominator, you are now dealing with a rational function. So a rational function has the form f of x is equal to some polynomial p of x on the top over some polynomial q of x on the bottom, but remember that q of x is not allowed to be equal to 0. X-intercepts is usually, well, I guess the first step, 1, is simplify. Simplify this as much as you can. Step 2 is find your x-intercepts. Your x-intercepts you find by setting p of x equal to 0 and solving for x. Step 3, your vertical asymptotes, you find by setting q of x equal to 0 and solving for x. Step 4, finding horizontal asymptotes. The horizontal asymptote is analyzing the degree of q of x versus p of x. So, highest order degree. So when you look at the degree of the highest term in p of x versus the highest term in q of x, if the degree of p of x is greater than the degree of q of x, you will have no horizontal asymptote. If that's like if you have an x cubed over an x squared term. However, if the degree of p of x is less than the degree of q of x, so you have an x squared maybe over an x cubed term, then you are going to get always the asymptote of y equals 0. If the degrees match up, so you have an x squared over an x squared term, then your asymptote is the leading coefficient of that p of x over the leading coefficient of q of x. The last step, step 5, is going to relate to step 1, where if you were able to simplify and there was a common factor, then you are going to have a discontinuity in the form of what we call a hole in the graph. So, holes are breaks or discontinuities in graphs. So to find these, step 1 is set the common factor that you factored out equal to 0 and solve for x. Set 2 is plug that x value you just solved for into the simplified f of x function and solve for y. So now you'll have your xy whole coordinate that you can put on your graph. Let's do a couple examples of this one. So if for this one I wanted to do x squared minus 9 over x plus 2, well, the first step is to simplify. Sorry, this is a little fuzzy, it looks like. But I can simplify this into being and x minus 3, x plus 3 over x plus 2. Doesn't look like this can simplify it all with a common factor, so at least I know that there's no whole discontinuities in this graph. I can, however, do my other things. So step 2 is finding the x-intercepts by setting my numerator equal to 0. So if I set x minus 3 equal to 0 and an x plus 3 equal to 0, I get one x-intercept of a positive 3 and one x-intercept at a negative 3. I can go ahead and plot those. 1, 2, 3. 1, 2, 3. Beautiful. Okay, my next step is vertical asymptotes by setting the denominator equal to 0. So if I set x plus 2 equals to 0, I get a vertical asymptote at x equals negative 2. 1, 2. And I'm going to go ahead and draw that line. Holes, we already determined there was none because there's no common factor. Okay, so the next step is horizontal asymptotes. That's by analyzing the degree of the top versus the degree of the bottom. So if I'm analyzing my horizontal asymptote, I have an x squared over an x. The degree on the top is definitely greater than the degree of the bottom. So if that happens, then I have no horizontal asymptote. So now I can say for my domain that I have x is equal to all x, except for it can't be the vertical asymptote. And for range, I get all reals because there's no horizontal asymptote and there's no holes. So now that I've done that, I'm going to create myself a little data table here to get a couple points. Maybe I'll do negative 5, negative 4, negative 1, 0, 1, 2. So if I plug in negative 5, I get, you can plug it into either the simplified or the non-simplified equation because they're both, to me, about the same level of difficulty. If the simplified equation is a lot easier, I'll always plug it into the simplified one. So if I get a negative 5 squared, I get 25 minus 9 is 16 over negative 3. So that equals a negative 5 1/3. If I do negative 4, I get 16 minus 9 is 7 over negative 2. So that's a negative 3.5. If I do negative 1, I get negative 8 over 1, so negative 8. If I do 0, I get negative 9 over 2, so that's negative 4.5. If I do 1, I get negative 8 over 3, So negative 2 2/3. And if I do 2, I get 4 minus 9 is negative 5 over 4. So that's negative 1 1/4. So I can plot some of these points now. If I go to negative 5, 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5 1/3. It's about there. To negative 4, 1, 2, 3, 4, and negative 3 1/2, 1, 2, 3 1/2. Negative 1. It's flipping to this side of my asymptote, and I get negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 0, negative 4 1/2. 1, 2, 3, 4 1/2. 1, negative 2 2/3. 2, negative 1 1/4. So it looks like this one is going to be coming in from over here and will run along the vertical asymptote. And this one runs along the vertical asymptote and then starts to head off that direction. Okay, let's analyze our next one. If I am simplifying the top, this looks like I will have an x minus 5 times x plus 1 all over x minus 1, x plus 1. So I do have a common factor of x plus 1 here, which means I will have a whole. Okay, so step 1 done, simplified. Step 2 is figuring out the x-intercept, and that can be done by setting the numerator equal to 0. So if I set my simplified form, because that's much easier, equal to 0, then I get an x-intercept at x equals 5. I'm going to go ahead and put that on my graph. 1, 2, 3, 4, 5. Now if I try to do my vertical asymptotes, I can set the denominator equal to 0. So x minus 1 equals 0. And I get a vertical asymptote at x equals 1. I'm going to go to my graph and draw that. Okay, next step will be figuring out horizontal asymptotes. So it's analyzing the degree of the numerator versus the degree of the denominator. You can look at the original function or the simplified function. Either way, you have a 1x squared over 1x squared or a 1x over 1x. They're both the same degree, and the coefficients in front of them are both 1 to 1. So we get y equals 1. And I can come over on my graph and draw that one. So my last analysis before I do a data table is figuring out this whole, because we have a common factor. So if I set the common factor equal to 0, x plus 1 equals 0, I get that the x-coordinate is negative 1. I can now plug that into the simplified equation to figure out what the y is equal to. So I have f of x is equal to x minus 5 over x minus 1. So if I plug in negative 1, I get negative 1 minus 5 over negative 1 minus 1. So I get negative 6 over negative 2, which is a positive 3. I'm going to go ahead and make sure I put that in my graph. So negative 1, 1, 2, 3. There's my whole. Okay. So for my domain, I'm going to have that x is equal to all x, except for x cannot equal negative 1, because I have a hole in the graph there, and x cannot equal positive 1, because I have an asymptote. For y, the range, I get that y cannot equal 1, because I have an asymptote there. Oops, why did I do that sideways? I don't know. And I get that y cannot equal 3, because that's where the hole in the graph is. Okay, so this one, you can do a data table to get some more points if you would like. Let's do negative 5, negative 4, 0, 2, 3. Hopefully that gives us a clear enough picture. If we do negative 5 in our simplified equation, because it's much easier, then I get a negative 10 over negative 6, and that will be a reduced down to 5 thirds. So I get a positive 1 and 2 thirds. If I do negative 4, I get a negative 9 over negative 5. So that's a positive 1 and 4 fifths. If I do 0, I get negative 5 over negative 1, which is 5. 2, I get negative 3 over 1, which is negative 2. And if I do 3, I get negative, oh, sorry, this is a negative 3. And if I do 2, I get a negative 2 over 2, which is negative 1. So if I go to negative 5, 1, 2, 3, 4, 5, positive 1 and 2 thirds, negative 4, positive 1 and 4 fifths, 0, positive 5, 1, 2, 3, 4, 5. So it looks like this will be hyperbola going this way. And then if I go 2, 1, 2, I get negative 3, 1, 2, 3. And I go 3, negative 1. So I get a hyperbola going that way. Okay, let's do 4 more examples of each kind, 2 that are reciprocals and 2 that are rationals. So for this one, going back to reciprocals, because you can see there's no x term on top, so it's not a polynomial over a polynomial, then we are allowed to just say, okay, we are going left 5, down 2, no reflection, and no stretch or compression. So I'm going to go down 2, left 5, 1, 2, 3. And I can draw my hyperbola in this one and in this one. Our vertical asymptote is x equals negative 5, and our horizontal is y equals negative 2. So that will shape what our range is and our domain. Okay, same with this one. It looks like we have no horizontal shift. We are shifting up 6, and we are reflecting and stretching by 2. So if I go up 6, 1, 2, 3, 4, 5, 6. I would be in the top right and bottom left, but this is reflected, so I'm going to be in the bottom right and top left for this graph. My domain, because there's no shift either way, oops. Is all x except for x cannot equal 0. My horizontal asymptote is at y equals 6, so my range is y is all y except for at that asymptote. Okay, 2 more examples to go. X plus 7 over x minus 2. Does not look like we can simplify this down, so step 2 is doing x-intercepts, which can be found by simply setting the numerator equal to 0. So we get an x plus 7 equals 0, or an intercept of -7. 1, 2, 3, 4, 5, 6, 7. Okay, next step is vertical asymptotes. That's going to be setting the denominator equal to 0. So we get a vertical asymptote at x equals +2. Horizontal asymptote, that will be our degree analysis. So we have an x over x, and that's a 1 in front of both. So we have our horizontal asymptote at y equals 1. Whole, well, there was no common factor, so there's none there. Our domain will then be only dictated by our asymptote, so that is all x except for x cannot be 2. And our range is all y, except for y cannot be 1. So now if we have a little data table here, let's go ahead and do, we already have -7, so let's do maybe -5, -3, -1, 0, and then positive 1, 2, 3, and 4. It's a little cramped. -5, -3, -1, 0, 3, 5. Okay, if we plug in -5, we get 2 over -7. -3, we get 4 over -5. -1, we get a 6 over -3, which is -2. 0, we get 7 over -2, which is -3.5. If we plug in 3, we get 10 over 1. If we plug in 5, we get 12 over 3, which is 4. So we go -5, 1, 2, 3, 4, 5, and barely a negative there, to 3, -3, 1, 2, 3, and again, just barely there. -1, we go -2. 0, we go -3.5. Now if we jump on over to 3, 1, 2, 3, it's going to be all the way up here, 10. And if we go 5, 1, 2, 3, 4, 5, that will be at 4, 1, 2, 3, 4. So we can draw this. And this. Okay, last example. Here it seems we can factor, so if we pull out a 2, we get x plus 1 over x minus 1, x plus 1. So we are going to have a whole discontinuity in this graph because there's a common factor. So let's run through the rest of our analysis. If we're trying to find the x-intercept, we will set the numerator equal to 0. So our numerator is 2. 2 equals 0. That is not true, so that means we have no x-intercept. For our vertical asymptote, we're going to set the denominator equal to 0, x minus 1 equals 0, and that is solvable for x equals a positive 1. For our horizontal asymptotes, we are going to look at the degree analysis, so we end up with a 2x over x squared, or a 2 over x. It's the same analysis. Our degree of P is less than our degree of Q, which means that our horizontal asymptote is simply y equals 0. Now to figure out our whole discontinuity, we need to first solve the common factor for 0. So if we set x plus 1 equal to 0, we get that the x-coordinate is -1. If we plug that back in to the simplified expression, we get 2 over -1 minus 1. Well, that is equal to a 2 over -2, which equals -1. So I'm going to go ahead and go -1, -1, and draw my hole in the graph. Okay, now we can do our data table to figure out some points here. I'm going to go ahead and do -2, -1, we already know has a hole there. So let's do 0. We'll skip 1 because it's an asymptote, so we'll go 2, 3, and see if we need any more points after that. If we plug in a -2 to our simplified equation here, we get 2 over -3, or -2/3. If we plug in a 0, we get 2 over -1, which is -2. If we plug in a +2, we get 2 over +1, which is +2. If we plug in a 3, we get 2 over 2, which is equal to 1. Okay, so let's go -2, 1, 2, and that's a -2/3. Remember, we have a horizontal asymptote at the x-intercept, so it's good that we're not crossing that. If we go 0, we go down to -2, so this one will be this side of my hyperbola. Then if we go +2, 1, 2, +2, 3, +1, looks like this. Be that side. So my domain, we have to keep in mind the whole discontinuity as well as the asymptotes. So we have that it can be all x except for x cannot equal a -1 because we have a hole there, and x cannot equal a +1 because we have our asymptote there. For the range, we have that y cannot equal -1 because our whole discontinuity is there, as well as 0 because we have an asymptote. So that is it for the review for graphing both reciprocal functions as well as rational functions. Go ahead and get started on your homework. I think it's 8.8, which is the review of graphing.